Hi, my name is Timmy. High pass filter is basically opposite of low pass filter, which allow high frequency to pass through and low frequency it will block. And then the third one is the band pass filter. The band pass filter will allow a certain range of frequency to pass through, and all the other frequency outside the range will be blocked. And then the last one is the band stop filter. It's actually the opposite of band pass filter, which will block the frequency in a certain range and then allow the frequency outside the range to pass through. So for me, and the theory part will be discussed by my partner.
Assalamualaikum. My name is Siti Maisarah. I will present about the theory. This project requires two important elements to be studied, which is lump element design and distributed element design. Lump element are those with fixed values such as capacitor, resistor, or inductor. Otherwise, a distributed element design is an electronic filter made up of transmission line length or other distributed component. First, this is the formula for the low pass prototype, and then for band pass, to design a band pass filter, start with a low pass prototype and then we convert to the band pass filter design. So there are two types of conversion, which is shunt capacitor conversion and series inductor conversion.
Hi, it's me again. So now I will be designing the low pass filter. So for the low pass filter, we need to design two types of design, which is the lump design and the distributed design. So first, let us talk about the lump design. So first one, let me use the laser pointer. Okay, so first one, we have the cutoff frequency of 2.8 gigahertz, insertion loss of 50 dB at 7.6 gigahertz. We have 3 dB equal ripple. Okay, and then after we calculate the omega over omega c minus 1 is 1.714. So by using these results, we can insert this result into this attenuation graph, and we can get that our order is a fourth order filter, which is n equal to 4. So after we decide our order, we can use the order to see the ripple element table, which is n equal to 4, and then we will use this 5 result, the G1 until G5. So for this one, we have 5G, so we will be using the pi combination to build our lump design low pass filter. So the schematic diagram is look like this. This is the capacitor and then the inductor with their own value. So this is the frequency response of the lump design low pass filter. So we can see at 2.8 gigahertz, the attenuation is negative 3 dB, and then in the 7.6 gigahertz, the insertion loss is negative 53 dB. So this is our desired results. So after the lump design, we need to design the distributed design for low pass filter. So the distributed design is a little bit more difficult, which is we need to use the Richards transformation to transform the value of the capacitance. So after transform, it will become like this. So this is the formula for the Kuroda identity conversion to convert the stubs. Okay, so after the conversion, you will get the normalized stubs. Okay, and then we times the value with 50 ohm, so it will become denormalized. So it will become like that. And this one is the expected diagram for the design, for the distributed design. Then this is the schematic diagram of the distributed design for low pass filter. And this is the frequency response of our low pass filter, which is at 2.8 gigahertz. We will get negative 3 dB attenuation, and then in 7.6 gigahertz we will get negative 53 dB attenuation, which is also our desired result. And the bottom one is actually the layout design of our distributed low pass filter. From this, so this is all from me. The band pass filter design will give to my partner. Thank you.
And then I will present for the task 2, which is design lump circuit for band pass filter. Okay, the center frequency that given is 2.8 GHz with 310 MHz bandwidth and maximum flat. We start by figure out the F1 and F2 for the provided center frequency. Since the n is equal to 4, the value of G1 until G5 were determined using the maximally flat table. And then the formula was then used to calculate the value of the series inductor and also the shunt capacitor. So here we can, for the shunt capacitor, I has been calculate the LK, C1, L3, C3, L4, and L5 and C5. And then for the series inductor, I has been calculate the LK, L2, C2, L4, and C4. The all of the value that has been calculated, I will use for the schematic circuit. So here is the schematic of lump band pass filter that has been designed from based on the value that we got from the previous slide, which is the shunt capacitor and series inductor. First thing first, we put the S parameter, which is for the start value, stop and step. We put the value that we got from the formula, which is for F1 and F2. And then we put the term 1 and term 2, and then we put the PLC1, SLC1, PLC2, SLC2, and PLC3. Okay, for the all of this, we put the value based on the value that we has been calculated from the previous slide, which is the shunt capacitors and series inductor. So we just put the value that we got, and then we run the schematic. So here the output of the lump band pass filter that we has construct, which is, so here we can see the center we got 2.78 giga. So the value is same with the center frequency that has given, which is 2.8 gigahertz. So from this we can conclude that we got the correct answer, which is we got the correct graph from what we calculate, and the circuit that we has been designed. Conclusion is microwave passive filter are fundamental building blocks in RF and communication system, which is allowing precise control of frequency spectra. By selective transmitting or attenuating specific frequency band, this filter enhance signal quality, suppress unwanted interference, and improve overall system performance. Is that from us? Thank you.